Okay, this is the second part, dealing with Chapter 8. I ran out of time here on the 8.5, calculating the lattice energy. Just a quick review. One of the things about calculating the lattice energy, this is all nice and cute, but really when we look at it, we look at the, we're looking at the energy with this, okay? And in looking at the final thing, the more charged that the ions are, there's going to be more lattice energy that's going to be involved. It's inevitable, okay? That's just the way it is. There's a payment for that extra ionization energy. And now we're going to shift. We got to shift into 8.6. We got to look at bonding. We have to talk about really ionic character. Now, there is this idea, in basic chemistry, we talked about the idea of, well, sodium and chlorine, bam, it's ionic bond, and that's entirely it. Well, really, the idea is that there's more to it than that, okay? There's most likely, this is getting into the theory, okay? And we don't have totally ionic bonds between individual atoms. There is a percentage of ionic character that we can compare the measured dipole of xy to the calculated dipole of x plus minus the completely ionic case. Okay? So we can have the measured xy divided by the calculated xy times 100, and that gives us the percent dipole in the gas phase. So when we're looking at the electronegativity difference and the ionic character, okay, here's what we're seeing. And I think this is really the big takeaway point that you guys need to pay attention, is that the more electronegativity difference you have, the greater the ionic character is going to be. Which would make sense, because if you think about it, when you're talking about connecting atoms together, they're going to form a bond, okay? And if we look at the ionic bond, well, how ionic is it? Okay? If there's a larger electronegativity difference between them, okay, then you have a greater percentage that they are ionic in nature, which would make sense. Okay? That would make sense. Okay, so really, I mentioned to you earlier about ionic bonds being more like extreme polar covalent. Okay, because at that point, what's the idea behind the ionic? Well, remember, there's a transfer of the electron that's there. So, some questions we have to ask is, if the bonds are not ionic, if they can't be, what are ionic compounds? How do we deal with polyatomic ions like SO3 with a -2 charge? Okay, so here's another way to look at the ionic compound. If the stuff is melted, then it conducts electricity when melted. Okay, that's a key thing. How do we tell for sure about an ionic compound? Well, if it's melted and it conducts electricity, then we know that it is ionic. That's another way how we define ionic. Okay, and that's it. We also use the generic term salt. Remember, people think about salt as sodium chloride, when in reality, it's typically a metal connected with a non-metal. Think about, your first two groups, your alkali metals, your alkali earth metals, connecting to something like chlorine, for example. Okay, that's something to think about. Now, what about covalent bond? Okay, so why is it, that they cause a group of atoms to act as a unit, as a group? Well, remember the idea about why is it that atoms are forming bonds? Okay, one, there's achieving stability. That would be a big one. And if you think about atoms like people, groups of people tend to function better, and there's more stability compared to people who are acting out individually. If you think about it, the family is a fairly stable unit. That's the perfect idea that God had, okay? As opposed to people being alone. God did not make people to be alone. Honestly, He didn't. Okay, and that's where family comes in. We're not talking about marriage here. We're talking about having a family unit. Okay, so because of the tendency of the atoms to achieve the lowest energy state, okay, so with more stability, you've got the lowest energy state when you're talking about these atoms coming together. Now, check this out. It takes 1,652 kilojoules to dissociate, break apart a mole of methane, CH4, into its ions. Now, here's the thing. If each hydrogen is connected to the carbon, the average energy to rip out one hydrogen from the carbon is about 413 kilojoules per mole. Well, that's not too bad. Now, here we go. We got CH3Cl has 3 of these CHs and 1 CCl. So the CCl bond, the carbon-chlorine bond, is 339 kilojoules per mole. And this is where we go through it. The bond is a human invention. Wait, what? You mean all this time we've been talking about bonding in chemistry, and you're saying now it's a human invention? Oh, yeah, it is. Remember the basic thing about the sciences, guys. We're trying to come up with workable models to explain what it is that we're seeing. That's the thing. So it is a way of explaining the energy change that's associated or connected with when we make molecules. Now, the thing is, the bonds don't exist in nature, but they are useful. In other words, it is a way to help us explain what is happening in nature. Okay? We have a model of a bond. So, what is a model? So we have a model of a bond. Okay, then what are we talking about a model? Well, it explains how nature operates. We get it from observations, and it simplifies and categorizes the information. The model has to be sensible, but it does have limitations. Ooh, that's a big major letdown, huh? Isn't it? Right. Science cannot explain everything away. It can't. With science, we try to get knowledge, we try to make models that help us explain what's going on. Are we going to get the ultimate explanation for everything? No, we're not, okay? And no, the Bible is not a science book. There are science truths that are pointed out in the Bible, okay? But it doesn't explain all the sciencey stuff. It is not, okay? And if they tell you it's a science textbook, they're lying. It's not, okay? It does point out science truths. But there are limitations to models. But the idea is that we try to explain what's happening. How do we understand that? Think about the history of the model of the atom. We had to sit there and alter that model as time went on. Why? Because we got more information. We got better at researching. We developed higher technology, better equipment to find out what was going on. And each person along the way gave a piece to our understanding of the modern model of the atom that we have today. And that's what I give as an example. Okay? So, if we look at this, we made some covalent bond energies. Here we go. Now, there's some simplifications. So, in other words, we are simplifying, we're making it a little bit easier to describe the bond energy of CH4. Now, each CH bond has a different energy. Okay? So, for example, CH4, we rip out a hydrogen, and we get CH3 plus H, and we get 435 kilojoules per mole. Notice it's a positive number because that means that's energy we have to put into it. It's an endothermic process. Now, to go and rip out the second hydrogen from this, now, it takes 453 kilojoules per mole to go and rip that out. Then we have CH2, we can rip out another hydrogen from it, and we get 425 kilojoules that we need to put in there. And then for CH, we finally rip out the last hydrogen from that poor sweet innocent carbon, okay? And it's got 339 kilojoules per mole. So, wait a sec. We looked at up here, if we look back here, we said it was 1652 kilojoules to dissociate a mole of CH4. So when we look at the average energy to rip out a hydrogen atom, okay, from this group of carbon and hydrogens, it's 413 kilojoules per mole. But for crying out loud, we're not seeing that it's an average. We're not seeing that. We're doing an average. This is the actual thing. Now, each bond is sensitive to its environment. Bonds can be affected, for example, by concentration. Bonds could be affected, more likely, by temperature. If you stop and think about it. Let's move on here. So here are average bond energies. Because this is the model that we can work with. We can work with averages. It makes more sense for us to do that. So we looked here, a carbon-hydrogen bond is 413. Now, we can look at a triple bond, like nitrogen, for example, and it's 941. Now, here's carbon monoxide with a triple bond, 1072. Oh. Now, here's another thing to think about. There is a bond length between the atoms. And that bond length is going to be determining what the atoms are and what does it take to get the lowest energy level to maximize that stability. That's the key thing. So when we're looking at the bond lengths of these individual bonds here, they're not all the same. They're not, okay? Now, the idea is, and this is an important one, the more bonds, that means you're going to get a shorter bond length. Ooh. Yeah. If you think about it, a single bond, you have a certain distance. Now, not all single bonds are going to have the same length. Okay? That's depending on the kind of atom that you've got. Triple bonds, now like a double bond, it's going to be a little shorter in the length there between two atoms. Well, how come? Well, because you got more electrons that are being shared, right? This isn't an ionic thing. This is, I'm just using covalent as the example here where they're sharing. So they're going to be a little bit more closer to it compared to a single. And triple, well, triple is very hard to go and break. That's what makes carbon monoxide so bad for us. Okay? Using bond energies, we can find the delta H for a reaction. Wait, Canu, what's delta H? Delta H, delta H. Come on, JR, you know this, man. Come on. Come on. Tracy, Alexis, Mariah, Gilbert. Anybody? Enthalpy, energy. Okay? I know Attridge tried to rise to the occasion, and that's okay. Okay? So, it takes energy to break the bonds, and you end up with atoms that are positive. We get energy when we use atoms to form bonds. That's negative. Okay? If we add up the energy it took to break the bonds and subtract the energy we get from forming the bonds, we get the delta H. Remember that energy and enthalpy are state functions. It doesn't matter. It's where you start, where you end. We don't give anything about where did you go in order to get there. I have to check my time here. 14 minutes. Okay. We're doing great. So let's take a look here for an example about energy. Find the energy for this. As it is right now, we're going to have to hold off on that. Okay? But if you think about it, you can go ahead and you got, that should be a plus. All right? And we'd have to check to see if this is all worked out, but we'll go with it. We're going to worry about this later. I can't worry about that right now with you guys. Okay. How do we explain bonding? How do we? Well, we have something called the localized electron model. Okay. Simple model because here's the truth, guys. We don't have a nice, cute explanation for how the atoms connect to each other that explains every part of how those atoms combine. We just don't. At this point, we can use the localized electron model. That's one way to look at it. The molecule is made of atoms that are bound together by sharing pairs of electrons using the atomic orbitals of the bound atoms. And this is one that's pretty, fairly easy for us to understand. You've got valence electrons using Lewis structures. You can predict the geometry using the VSEPR, okay, and the description of the types of orbitals, which we're going to get into the next chapter. Okay, so we can use the localized electron model, and that's one that I have been basically working with you guys on. Okay, when we covered chemistry and honors chemistry, and even to an extent here in AP Chemistry. Lewis structure, okay, pretty much we're looking at valence electrons. How are they arranged? One dot for each valence electron, okay. Stable compound has all the atoms with a noble gas configuration. Hydrogen follows the duet rule, meaning it's got 2 electrons to be full. Okay, the rest follow the octet rule. Okay, and the bonding pair is the one between the symbols. Okay. We sum up the valence electrons, use a pair to form a bond between each pair of atoms, arrange the rest to fulfill the octet rule except for the H and the duet. We can look at H2O, for example. Okay, a line can be used instead of a pair. That's fine. We can do that. All right. Useful equations. Okay, guys, I would sit there and I would say to you, when we're looking at this, I'm not going to worry about the happy half divided by 2 equals bonds. I am not going to worry about that. Okay, I am going to look at here, what do we look as the central atom? Because that's the thing that we have to look at here. I only have a couple of minutes left. Okay? So, POCl3, P is the central atom, SO4, S is the central atom, and so on. Okay? Well, what about exceptions to the octet? And I think that's where I'm going to probably start winding down here. Exceptions. BH3, boron trihydride, okay? Be, beryllium and boron often do not achieve an octet. Well, why is that? Because they are small. They're small atoms. They have less than an octet for electron deficient molecules. SF6 is one that it can take more than 8 electrons, okay? Third row and larger elements can exceed the octet, and we can use the 3D orbitals for that, like I3 with a minus. Exceptions, if we have to exceed the octet, the extra electrons always go around the central atom, like ClF3, XeO3, ICl4, BeCl2. That does happen. They are the exceptions to the rule. But generally speaking, we go with either 2 or 8. Okay, I am going to stop here because I'm running out of time. All right, guys, I will catch you later.